we now have Hadi Nahari, and will tell us about singular Riemannian foliations and I-Poisson geometry or one-Poisson geometry. I-Poisson geometry. Okay. You have until a few minutes before 3.
Okay. Thank you, and thanks to the organizers for giving me this opportunity. So let me start with a overview of what I want to talk about today. We have 3 sections. The first section, we talk about the category of singular Riemannian foliations, and we define an equivalence relation, which we call it Morita equivalence. In section 2, we start a seemingly different story. We find the category of I-Poisson manifolds, or one can say singular constraint systems, where its objects are actually Poisson manifolds together with an ideal of a smooth function satisfying some property. And in section 3, we will see the marriage of the first 2 sections. Okay. Actually, we define a functor opposites. Yes. So maybe I can do it like this. Okay, actually we define a functor capital phi from the category of the sub F's to the category of I-Poisson manifolds. Yes. So first, let's start with the definition of singular foliations. As you may know, it's just a pair M-F, where M is a smooth manifold, and F is a submodule of the smooth vector field, which is locally finitely generated and also evolutive. Seems that again I should use this. How can I zoom out? Yeah, it works better. So, a theorem of Lambert-Herman guarantees that such a submodule decomposes our manifold into connected injectively immersed submanifolds called leaves in foliation theory. And note that here, as you can see here, the leaves can have different dimensions. Then we define the notion of pullback foliation under submersion. So assume that you have submersion from N to another smooth manifold M, and we have a singular foliation F defined on N. So we define a submodule of smooth vector fields on N, named pi inverse F, to be generated by projectable vector fields projecting to F. And by projectable vector fields, X here, we mean vector fields such that there existed another vector field V on the base, such that this vector field X projects pointwise to V. And then Androniakis and Skandalis prove that this pi inverse F is actually a singular foliation. Okay. Also, let's start with the functions. Sorry. Yeah. Actually, we can also define it for more general maps. If this is smooth map is a transversal map, we can define this full map. But here I only need submersion. So
submersion.
Yeah. So let's start singular Riemannian foliations or SRFs for abbreviation. I present 2 definitions. The first one, which is a classical notion, is called geometric SRF. And then I go to the more recent definition, named algebraic SRF, and note that they are not so algebraic. It's just to distinguish them from the first definition. So here you can see the definition of the classical definition of geometric SRF. It's triple NGF, where NG is just a Riemannian manifold, and F is a singular foliation on this Riemannian manifold. And in addition, we have a compatibility condition between the singular foliation and the Riemannian structure. And this compatibility condition is that for every geodesic which starts orthogonal to a leaf, it should remain orthogonal to all the leaves it makes. But here we prefer to work with this more recent definition. All the assumptions are the same. We only change this compatibility condition. This compatibility condition is that for every vector field in our singular foliation, we should have that the Lie derivative of the metric in the direction of the foliation should lie inside the symmetric tensor product of differential forms on M and the image of our singular foliation under the musical isomorphism G flat. But later we'll see another equivalent definition. So let's mention two important facts about this new definition. The first one is that proposition 1 says that every algebraic SRF defined as above is also a geometric SRF. We'll see it at the end of the talk. And proposition 2 says that if we have a Riemannian submersion from Riemannian manifold N, H, 2, and G, and we have an algebraic or geometric SRF, NGF, on the base, then the pullback foliation pi inverse F also defines an algebraic or geometric SRF. So let's start with the equivalence relation. It's actually inspired by the notion of paucity of Morita equivalence for singular foliation, introduced by Alfonso Garmendia and Marco Zambo. And similarly, the goal is to define an equivalence relation, as I mentioned.
Sorry, you said the implication works one way, does it work the other way?
No. There is an example that I can explain at the end. So let's go to the definition of this equivalence relation. We assume that we have two algebraic or geometric SRFs, M1, G1, F1, and M2, G2, F2. We call them Morita equivalent if there exists a Riemannian manifold NH and two Riemannian submersions with some properties, pi 1 and pi 2, which are in fact surjective, Enrichment complete, and they have connected fibers. And by enrichment complete, if you don't know, I mean that for every smooth curve on the base, we have global horizontal leaves on the top, starting from this very point on the fiber. And the second requirement is exactly requirement for the definition of paucity of Morita equivalence. We require that the pullback foliations from both legs coincide on N. Okay, so the natural question is that why is this equivalence relation? The proof is, again, similar to the proof for paucity of Morita equivalence. Self-equivalence and the flexibility are easy to show by definition. But the thing which is more difficult here is the transitivity, because let's look at the next slide. This is our situation. We have M1, G1, F1. For transitivity, we have M1, G1, F1. Morita equivalent to M2, G2, F2 by means of H, U, H, U. And M2, G2, F2 M3G3F3 Morita equivalent by means of WHW, and we want to show that the first and the third are Morita equivalent. So here we take the final product of U and W over M2, the name is N, and so it's we need to define a Riemannian metric here to make this here projections to U and W Riemannian subvalues. The fact is that the pullback of this matrix on HU and HW to N is not enough. We need to subtract the metric on M2 by this map, by this composition map F, and this metric does the job. And the rest is the same, but by an easy diagonal chasing, you can show that the pullback foliations also coincide. Okay, so here I will show you just a part of a theorem by Alfonso Garmendia and Marco Zambon that for Hausdorff-Morita equivalent singular foliations, we have homeomorphic Lille spaces, and you can define this homeomorphism. And our definition is just the definition of Hausdorff-Morita equivalence by adding some conditions. So if you have two Morita equivalent singular Riemannian foliations, algebraic or geometric, then the underlying singular foliations are Hausdorff-Morita equivalent, and we have this homeomorphism between the Lille spaces. And we can improve this theorem to theorem 1, which says that if two algebraic or geometric SRFs, M1, G1, F1, and M2, G2, F2 are Morita equivalent, then this homeomorphism between the Lille spaces actually preserves the distance between the leaves. And in particular, if the Lille spaces are smooth, then they carry Riemannian metric, and this homeomorphism will be Riemannian isometric between these two. So this is the first invariant of our equivalence selection. So this was the first story. Now I can start the second one, I-Poisson manifolds or singular constraint systems. So before going to the formal definition, I want to present an example. So here we know this example. It's quasi-isotopic reduction. We take symplectic manifold S omega. We take a quasi-isotopic submanifold C inside it. And let IC be the vanishing ideal of C, ideal of functions vanishing of C. And as C is quasi-isotopic, this ideal IC is closed under Poisson bracket. It's a Poisson subalgebra, smooth function on S. And then we can look at the Hamiltonian flow. And if the quotient space is smooth, we know that this quotient of C with respect to the Hamiltonian flows gives the quasi-isotopic reduction, which also inherits a symplectic form. But this is the regular case. So we want to do the same thing in the singular case. So let's define I-Poisson manifolds. Okay, by I-Poisson manifold, we mean P with its Poisson bracket, the Poisson manifold, and an ideal I, where this is an ideal of a smooth function, which is locally finitely generated and also a Poisson subalgebra. But here note that for this ideal I, we can construct this vanishing set C. But you can see in general, it is not a smooth manifold. It can be a very singular set. So we cannot do the reduction as before, and we will do it in an algebraic way. Okay, to do this, we define the Poisson normalizers of our ideal I, name it Ni, defined, as you can see here, functions f such that the Poisson bracket for every element in the ideal again lies in the ideal I. Or in physics, they are called Dirac observables. Okay. The first property, and the most important property about this formalism that I want to use here is this proposition 4, which says that if we have an I-Poisson manifold, P with I, the ideal I, and we take a function f in Ni, then the Hamiltonian flow of f preserves the ideal. And note that this proposition shows the importance of having this condition on I to be locally finitely generated. If we don't have this condition, this proposition does not hold anymore. As you can see in this example, we can take your Poisson manifold to be T star R with standard Poisson bracket. You can define your ideal I to be defined by functions vanishing on R negative, smooth functions vanishing on R negative, as you can see in the first drawing. And here, I is not locally finitely generated. So let's see what happens. We have, we can look at these functions, H, Q, P equal P, the momentum coordinate function, which is inside the normalizer of I, because its Hamiltonian vector field is just dq, and it preserves the ideal. So its Hamiltonian flow is just translation by t in time, and it does not preserve the ideal, as you can see. It moves it to the left. So this condition to be locally finitely generated is crucial. Okay, I will mention some properties of this normalizers. First of all, by Jacobi identity, Ni and also the quotient Ni over I are Poisson algebras. So we define the Poisson reduction of our I-Poisson manifold Pi to be the Poisson algebra and I over I. Just as a remark to see what's the load of this ideal. In the case of Master-Weinstein reduction, if we take C to be the pre-image of 0 under the momentum map, and taking I to be the vanishing ideal of C, then this Ni over I will be Poisson isomorphic to the smooth functions on the reduced space, with Poisson bracket induced by the inherited symplectic structure. Okay, so to define the category, it remains to define the morphisms. The morphisms are not Poisson maps. They are somehow a relaxation of Poisson maps. So we define an I-Poisson map to be a smooth map from an I-Poisson manifold P1 I1 to another one P2 I2, which satisfies these three properties. That first of all, we require this the pullback phi star to preserve the normalizer and also the ideal. And for every two functions in the normalizer of I2, we require this third condition, that the Poisson bracket of phi star f and phi star g on P1 subtracted by phi star of the Poisson bracket of f and g on P2, which is required to be 0 in the case of Poisson map, we require it to lie inside the ideal I1. So this is not a Poisson map, but on the vanishing set of I1, it is. And note that if both I1 and I2 are 0, then I-Poisson map will be just a Poisson map. So let's see what we will have after these conditions. The first condition gives this map, phi star from Ni2 to Ni1. The second condition, we can use it to say that this map descends to a map phi tilde from the Poisson reduction of the second Poisson manifold, E2I2, to the Poisson reduction of the first one. And the third condition gives this proposition 5, that if we have an I-Poisson map between two Poisson manifolds, then this map phi tilde gives a morphism of Poisson algebras between these Poisson reductions. So this is the end of the second story. So let's see the marriage. So I want to define this phi to a capital phi from the category of singular Riemannian foliations to the category of I-Poisson manifolds. Here I send the objects, where the objects of the first one are just algebraic SRFs. Here I restrict to algebraic SRFs. And I send it to its cotangent bundle with its standard Poisson bracket. And I define an ideal IF associated to our foliation F. So what is this IF? You can view elements in the singular foliation, which are vector fields, as functions on the cotangent bundle. So you can take the ideal generated by these functions, and note that this correspondence going from vector fields to functions on the cotangent bundle is actually a morphism of Lie algebras. Using this fact, we can show that IF is closed under the Poisson bracket, and as F is locally finitely generated, we can say that IF is also locally finitely generated. So from every algebraic SRF, we can get an I-Poisson. So what about the morphisms? Here we didn't use the metric at all, but to define the morphism, we strongly use the metric. And we define the metric like this. The morphisms of the first category are Riemannian submergence from N1G1F1 to G2F2, two objects, with the property that this Riemannian submergence preserves the algebraic SRF. The pool map of F2 equals F1. So how do we get this map? We have a bundle map from the tangent bundle of M1 to the tangent bundle of 2. Then we can use the metric on both manifolds to identify the tangent bundle with the cotangent bundle, and it induces a bundle map from TSR M1 to TSR M2, which we name it phi pi. So, and finally, we can show that this map phi pi is in fact an I-Poisson map, and so this phi defines a function. So it's a special case is when this phi pi is a Poisson map. Proposition 5 says that if phi pi, phi pi is a Poisson map, if and only if the horizontal distribution of our Riemannian submersion, which is the orthogonal complement of the vertical subbundle, is integrable. So this map is not Poisson map in general. And in the next page, I have an example where, due to the lack of time, I cannot explain it, but I have an example of Riemannian submersion where the horizontal distribution is generated by these two vector fields. Many of you know that it's not evolutive. And so the horizontal distribution is not integrable. And the map phi pi with this, where you can see this fourth component, and you can see that it's not a Poisson map, but an I-Poisson map. I can explain this example if anyone was interested later. So, an interesting fact about this marriage is that if we have two Morita equivalent algebraic SRFs, then the associated Poisson reductions and IF2 over IF2 and IF1 over IF1 are isomorphic Poisson algebras. So here we have an algebraic invariant of the Morita equivalence. Okay, here in this page, I will present an equivalent definition for being an algebraic SRF after all these considerations. First of all, note that for every Riemannian manifold, the Riemannian metric G defines a Hamiltonian function, a standard Hamiltonian function on the cotangent model. In double coordinates, the local double coordinates is like this. It's 1/2 of Gij, inverse of the metric, Pij. Yeah, these are momentum coordinates. And lemma 1 says that a singular foliation F on a Riemannian manifold Mg defines an algebraic SRF if and only if Hg lies inside the normalizer of F. This is the equivalent definition for this recent definition of algebraic SRF. And if you want to see why is this true, look at this equivalence between these two equations. Actually, Hg is a function which is quadratic in momentum coordinates. And you can view it as a section of S2Tm. And so our condition is equivalent to this fact that the Lie derivative of this section, Hg, in the direction of every vector field in the foliation lies inside the symmetric tensor product of vector fields on M with the foliation F. And then you can apply our functor again, and you will get this condition. Okay, I have 5 minutes, so to finish the talk, after all these considerations, I can present a somehow tautological proof of this proposition one, that every algebraic SRF is a geometric SRF. So for the proof, look at this situation where we have our algebraic SRF on M, on the Riemannian manifold Mg. These red curves are our leaves. And we want to show that for every geodesic starting orthogonal to a leaf, it remains orthogonal to the other leaves it meets. So how do we do it? We apply our functor, we get our cotangent bundle and ideal IF, and let's see the vanishing common set of the ideal IF. And as you can see, it can be singular. So let's say something about this C. What is this C in fact? This C consists of points QP into M, such that for every vector field in the foliation, if we apply the covector P to the vector field V evaluated at Q itself, it's by definition of IF. So the C is in fact the annihilator of F. And if a geodesic is orthogonal to a leaf, so what happens if we look at the tautological leaf to the tangent bundle, gamma gamma dot of the geodesic, and then apply the musical isomorphism to it to get curve in the cotangent bundle, by this consideration, it means that the curve intersects C. And what do we want to show? We want to show that if such curve intersects C, it should remain in C. And the situation here for this orange geodesic does not happen. Where it intersected it and it does not lie here. So this is what we want to show. But we have it because it's the Hamiltonian flow, the image of the geodesic flow under the musical isomorphism. So these are this image that I mentioned here are just Hamiltonian flows of Hg. And our equivalent condition is saying that Hg is inside the normalizer by F. And proposition 4, that you can guess what was it here if you don't remember, says that because Hg is in the normalizer by F, its Hamiltonian flow preserves by F. So it also preserves the common zero set C. So if it intersects C, it remains in C. And so if we have an algebraic SRF, we have the geometric SRF. That's it. Thank you for listening and for your attention.
Thank you, Hadi, for the nice talk. Joao, any questions online?
I think I have one, but let me wait for a second to see if anyone else has some.
Sure.
Well, that does not seem to be the case. So I'll just ask something. I'm not completely sure if I understood from the definition, but if I recall correctly from literature more focused on really just singular Riemannian foliations, they often define the singular Riemannian foliation in terms of the partition by leaves. While for singular foliations without Riemannian structure, usually we take the submodule. Do you have a feeling for whether somehow, how should I put this? If you have different submodules, they still have the same leaf space, which is one of the invariants of the Morita equivalence. So do you know how likely is it that you can pass from different singular Riemannian foliations in your sense to the same one in terms of the partition via Morita equivalence?
You mean we have, let me, if I understood correctly, you mean that we have the same singular foliations, but with different metrics?
No, sorry, no, with different modules of vector fields. But just
actually, if you change the module, an algebraic SRF, it's possible that it does not remain algebraic SRF. I can give you an example. For example, if you look at rotations in R2 generated by x dy minus y dx, these are killing fields, and they trivially satisfy our condition. It's an algebraic SRF. But if you multiply this generator by x squared plus y squared, it's not an algebraic SRF anymore.
I see. Okay, thanks. There is another question online from Pingsu. If you could unmute yourself, please. Ping?
Yeah, well, I just wonder if it's, what about a regular foliation case? So what is the implication? I mean, I never seen this before, just for the regular foliation. Before you jump to single foliation, what is the state of art for regular foliation?
In the case of regular foliations, these two definitions are
no, for this this category. I mean, I try to understand what is the point of this different category or those things.
When defining this category of I-Poisson manifolds.
Yeah, because I saw that the point is you try to marriage two different categories, and I'm trying to understand what about regular foliation case. So what are the
things? I skipped many things here. For example, let me go back to proposition 2. Actually, most of the proofs that we have, properties that we have for this new definition, we prove them through this category. We first apply this functor, we went to this category of I-Poisson manifolds, and then we prove them there. For example, like in proposition 2, here for the geometric case, it's just an exercise of Riemannian geometry to show that the pullback of a Riemannian foliation remains a Riemannian foliation. But for the algebraic case, we couldn't at least prove it directly. And we apply this functor, So this was one of the advantages of this functor. And also, the other goal was to find this Poisson reduction. We wanted to define an invariant for our Morita equivalence, and this machinery helped us to define this normalizer. As you can see in theorem 3, this is also an advantage of going to this category.
Yeah, my guess, I guess what I'm trying to ask is what is really the motivation you want to? I mean, this two different category, or just you want to? Does that help to understand something? The single foliation, regular single foliation, or
both to understand the singular Riemannian foliations, and also for some physical motivations. If I understood correctly your question, this equivalent condition says that if this IF, if the generators of IF are giving gauge equivalence sets, then this condition in this machinery going to this I-Poisson manifolds means that this HG is actually gauge equivalent, gauge invariant. And so, and actually this condition first appeared in a paper of Thomas with Alexei Kotov. So the motivations are from both sides. And also, there is something else about this category that I didn't mention here. And it's that we were also interested to somehow extend the definition of Morita equivalence for Poisson manifolds. We are also trying to define a notion of Morita equivalence for I-Poisson manifolds, such that in the case of these ideals being 0, gives your notion of Morita equivalence.
Hadi, we should maybe wrap it up, I think, because we are already over.
Sorry.
So let's postpone further discussion, I guess, and we resume at 1/4 past. Okay.